So we'll wait for 1 or 2 minutes more and then we can start today's discussion session. I think I'm audible, right?
Yes, yes.
Okay, thank you. Thank you. Okay, so let's begin with this week's discussion. This week mostly what professor has discussed regarding the basics of power of distribution system operation, one of the basics of power distribution system operation, and the major thing that lies as the backbone of this entire power system operational framework in planning studies in economic or reliable operation of the distribution system is to perform the load flow in the distribution systems. Okay. So is to perform the load flow. So load flow forms a which already we have learned how to model things, how the distribution system networks are modeled, how they are structured, and based on that, once we have all these things, the topology information, the system of the line parameter information, so all these things we have known. So okay, so there are various types of connections that we need to keep in practice, and also the types of outages and the schemes that or the metrics or the indices that we need to take care of whether they are violating the threshold or not. So considering things, so considering all these things, the major the basis of understanding the distribution system operation or planning purposes is to get through the load flow activities. Okay, so already we in the UG courses we are mostly accustomed with the load flow analysis or load flow studies or power flow analysis, whichever may be the terminology used as per the books. So the need of power flow needs to be taken a good care before means the basis of the understanding of why we need to perform power flow, that needs to be clarified. So already sir has discussed in his lectures, but still I would firstly go through the basics and then we will switch on to the question answers Q&A sessions for the assignments in the last session or the last semester and last to last semesters and the assignments from the other courses, other semesters too. So mostly the understanding of load flow is already we know that the power flow is mostly a nonlinear problem, right? So mostly it's a nonlinear problem and it has the number of known and unknown quantities are mostly it is the value that we need to determine for the unknown quantities based on the information of the known quantities. Okay, so there are unknown quantities. What are those unknown quantities? Voltage magnitudes and phase angles. So these two things needs to be known because these two forms the basis of which the states. We can say these two can be considered as the states of the entire system in operation. Okay, this V constitutes of all the vector of all the these these is a vector. You can represent it as a vector where V constitutes of all the voltage magnitudes, all the voltage magnitudes of, so it's better to write the voltage magnitudes of all the nodes, and this delta is the means delta is a vector, but it constitutes of all the phase angles of all the nodes. So once we have the information of these states, like the base states of the distribution system, so what's the need of performing this or performing this load flow? What we can do is that once we have the information of all these voltage magnitudes and phase angles, we can reconstruct the entire power system. Means reconstruct means how to reconstruct the statement is in the way that we can reconstruct the power flows. If the power flows in the lines, power injections at the buses. So, and what is the need of finding out these power flows or power injections? There has to be a certain a specific need, right? So the need is we could have done anything else, but why are we could have been satisfied by finding the voltage magnitude and phase angles only. But the need of finding these power flows is that since the power is getting transferred from one area to another area, or one of the substation to the load centers, to the loads, to the distribution side feeders, which laterals from the substation to the laterals and flowing through the, towards the customer mostly. So, because now in the DER integrated scenario, power can be bidirectional, but mostly over the entire day, if we can see that mostly the power flows from the substation to the uh, customer end. Although this system was unidirectional up to the integration, when the integration of these DERs became on a major scale, there can be situations where the opposite things may happen, because sometimes load may not be the same as the load demand, or the generation end. So there might be cases when load demand is lesser than the generation. So in those cases, the direction of power in any line can be bidirectional, means from one generation to delivering to the other generation. So this is the need of these power flows. So by performing the power flow, we can say, or we can find out whether there is a overload in the line, because there are certain constraints. That is, the overload limit need not be exceeded by the power flow, means by the current, because there is a thermal limiting capacity of the cable, or the conductor. Okay, so thermal constraints are there, and that may lead down. There are constraints related to the settings of the equipment, settings uh, of the protection equipment. So, this is mostly the understanding of load flow. Now, one question is, already we have heard, or we have learned that this is the load flow is related to the mostly related to how the system would be operating in, mostly in it's kind of a planning studies, right? So the it's kind of a planning study. So based on that, we can see, or we can analyze whether the stability of the system can be maintained or not. Means the distribution system here, considering, or we can say the power systems also, system can be maintained or not. We can. So the question is, where we have another thing, another operational, uh, we can say operational tool, power system operational tool, operation tool, that is also known as state estimation, right? And the power entities, means the power companies, maybe TSOs, DSOs, anything, utilities. So they, in the transmission side, in the distribution side, the output of the state estimation is also giving us the value of V and delta. Okay, and already we have understood, or we have learned that load flow is just for a good understanding why and how the things are, individual things are, have their own importance. Okay, so that's the major aim of myself discussing the difference between these two. So this this load flow also gives the value of V and delta, and also state estimation also gives the value of V and delta. So any basic understanding what's the difference here? Because we are getting, then why we should perform load flow, right? And why we should perform, if one load flow, one is performing load flow, then what's the need of performing state estimation? And if someone is operating or running state estimation, what's the need of performing load flow? That's my question. So if you want a few the answers, so you can. Otherwise, I'll discuss the same. Okay. So, uh, because forget about the three-phase and single-phase. Consider that all are balanced. Although we know that distribution system is not balanced, and the transmission system is balanced. Transmission system is a balanced, mostly balanced because of the transposition of the conductors being transposition of the conductors being performed at a regular intervals. Although in case of distribution system, things are not balanced. Things are unbalanced in nature. So, so for those who have joined now, my question here is, we know that load flow, after performing load flow, we are getting the results of voltage magnitudes and phase angles of the entire distribution systems, or we can say distribution or transmission, anything. But consider the distribution system since the course is based on the distribution side. And also, if you have any kind of knowledge of state estimation, because it's also taught in UG course, just a simple overview, not in a broader sense. But if you have any idea, then you can brief on, because the output of state estimation is also the voltage magnitudes and delta. So what's the difference between them? Any idea? If one of you can have any idea, so you can share. Otherwise, and then we can switch to the assignment questions, because that will be of use.
This for a radial network and the unbalanced system.
Yes, these are the basic overview of how a transmission system is looks like, or mostly it's a balanced, and because of the transposition, but distribution system is mostly unbalanced. This has no relation with the question. This is just for this. This is the question, that what's the basic difference of state estimation and load flow, because both of them give the value of voltage magnitudes and phase angles of all the nodes of the entire system. Okay. So since we are getting, so what's the need of performing both, because in power system both of them are performed simultaneously. So what's the need, if one is also only from load flow we are getting V magnitudes and phase angles of all the nodes, so what's the need of performing estimation, state estimation? And if we perform state estimation, then what's the need of performing load flow? Any idea what state estimation is? Any idea?
For me, no, sir.
Yes. For okay. Yes. Okay. I'll detail. Okay. So just I'll give a basic understanding that we get the same things from both of these, right? By performing both these activities, both these operational, these mostly this is power system operational or distribution system operational scenarios or context here in this course. So from the load flow, as we all know, that load flow load flow is used for, already professor has taught. It is used for mostly planning, right? Mostly planning studies, operational studies, and we can say, or economic operation, we can say. No, writing it. Operational, most economic operation. And okay, that's the, and later on using this load flow we can understand whether the system is in stable operating mode or not, and some contingency analysis we can perform based on the load flow, whether system is out of operation or not, and any equipment out of operation of any equipment, how the system will have an impact, uh, what will be the severity of that impact of, or severity of that equipment being uh, out of the entire distribution system. If any equipment is outage in outage condition, or any line is any outage condition, then how it will impact the severity of the remaining part of the system. So all these things we can perform, and we can take the help from load flow. The basic understanding and of state estimation is, the state estimation is real time. Okay, state estimation is performed in real time. It's a real time monitoring exercise. My question was just to give you an idea why, what's the basic difference of these two. Okay, because both of them give the same information, but the difference is it gives the real time it's a real time monitoring exercise or distribution system monitoring exercise, and it takes the help of all the data, all the data, or we can say use the data from the sensors placed in the distribution system. So it takes help of the measurements. It, on the basis of the measurements, like here we have, it's a, let's consider this as a power system. Here we have a control, this is a control station, let's say. Okay. This is a control station, and here we can say numerous sensors are placed. Sensors are what? Sensors are RTUs and SCADA, or RTUs, SCADAs, or we can say smart meters in the distribution system. RTUs, club, we can say distribution DRTUs, distribution system RTUs, distribution system PMUs, and this is the control center CC. So information is delivered to the control center from each of these sensors, and based on the information received from each of these sensors, the control center has the high computing computers. Okay, so based on these computers, these based on the information processed in these computers, means the state estimators delivers the output of real time operating voltage magnitudes and delta. But these, and there are some noise associated, but that is in more detailed form. I'm not trying to go much of a detail, but mostly the sensors have there also the noise, and they, because some sensors may give redundant, their bad measurements too, but we need to filter out, and that is the work of a state estimator, and the output is to have a practical or real-time operational uh, overview of the entire distribution system at each point of time. Means, suppose performing the estimation in 5 minutes of time, we perform this estimation in 5 minutes of time. But load flow, and once we get this V and delta, we can see whether any line overload limit has crossed and all these things, and based on that we can take the best possible way, or best possible, we can say, we should try to take the best possible action, so that the system operational continuity prevails for the entire period of time. Okay, and from the load flow we have the information of these power values. Here, what are the basic requirements of load flow? Any one of you can just what are the necessary things to perform load flow? Means necessary things in the sense that which of the power values needs to be known, and any idea. I think load flow you have come to. So in load flow, we need to have what values, which values like power, voltages. So in load flow, we need to have the values of the voltages, powers, and what are these voltages or powers? Means we have three types of buses, right? PQ, PV, and slack. So PQ buses, we need to have the information of P and Q, and mostly the entire system is of PQ buses. Okay, some are PV buses because, or we can say these are the generator buses. Okay, and a slack bus is there to cater the losses of the entire system and the required amount of generation and load mismatch. Okay, so PQ buses, in the PQ buses, we need to determine the other two quantities because we have V, delta, P and Q. These are the four quantities out of which in PQ buses P and Q are known. So V and delta needs to be found, and in PV buses we already know the value of P and V. Although there are constraints in P and V, the values can't exceed a certain limit. There are limitations where the line or the reactive power, there are limits in the reactive power too. If it violates, then PV buses becomes PQ buses because the Q limit is violated. So, like this, we perform the iterative load flow. And let's say, in PV buses, the information of Q and delta needs to be found, and in slack buses it is the values of V and delta are known, so we need to find out, means if nothing needs to be found out for slack buses, so mostly it will take care of the P and Qs, means the remaining P and Qs, that is the losses, system losses, that is line losses, and the load mismatches, load generation mismatches. Okay, so it will deliver the remaining P and Q based on these P and Q and the difference. These are the generations, and out of these generation and the P and Q, this is the load demand. This is the generation, and these mismatch of these load and generation and the different the line losses needs to be catered by the slack bus. So these are the values of, and from where do we get these P, Q? Any idea? These are obtained from the various power system of exercise like automatic generation control. Q is to reactive power. Sorry, Q can be obtained from uh, real power loss minimization. This exercise is performed to get the value of Q, the this PQ value. So what we need to know is that all these things can't be obtained in real time. Okay, all these exercises are performed for the next day. Means for today, we have previously in week one or two, I think I've discussed that economic load dispatch, unit commitment, all these things. So from the unit commitment, economic load dispatch, we get to know the values of these P and Q so that the cost is minimized. Okay, and based on that P and Q, all the information we now have, all the information to perform a load flow. So today's step, while we have the information, while we are performing the state estimation in per 5 minute instant of time, all these P, Q and all these values are not at all required. We have a nonlinear equation of the measurements obtained from the sensors in the distribution system or transmission system, you can say. But here, since we are discussing distribution system, so let's consider these are the distribution system. So we are getting the information from the sensors. There is a estimator running in the control centers. It's like a firewall, and when we have the sensors of the measurements from one side, the output side we get the values of the magnitudes and angles, and based on which we can say that whether there is any violation of the system line overload limit and all these things, and accordingly we can take the necessary action. So this is a real-time operational exercise, and is of great importance in power grid also. In Kosovo, the state estimators is run. The estimators run at NLDC, National Load Dispatch Center, Katwari Sarai, in Delhi. So there the information we have, but here in load flow we forecast the 15 days ahead values. Okay, so the 15 days values. Uh, okay, sorry. These two would be for these P and these V. Okay, and not for, because these are the generators. So automatic generation control is for this P, and this V is for this one. Okay. Yes. This P and Q is obtained from forecasting. This is for, this arrow is going for PV. So this is for V, this is for P. Okay. Now, sorry. And these two we get from load forecasting. And load forecasting is done for P and Q for the next day. A day ahead forecasting, real time forecasting is also done from 15-minute basis, but that's not the for the planning activities. We need to perform it a day ahead, or suppose there would be a contingency, some generator would be on an outage phase for some point of time, or a day, or a fifth, or for half of a day, means 12 hours. So how the outage of a generation, because it might be going for maintenance, periodic scheduled maintenance. So according to with the outage of a generator, suppose a 500 megawatt, how the power system would operate. In case of distribution systems too, we can also say that would be of a lower scale, but the operation would be same. So the load flow is performed to get an overview how the system or the power distribution system would operate a day ahead, a week ahead. Okay, so so that we can plan accordingly, but the exact operational overview or the operational perspective can be obtained or can be clarified from the values obtained from state estimator. So I think, is it okay or is it clear? Because here also we are getting V and delta, but this will help us to prepare for future. And this V and delta, as we are obtaining, this will help us to prepare for the current scenario, for the current point of time. And this is for mostly plan for future. Okay, that's the basic difference. So here it's not a real-time exercise, and this is a real-time exercise. State estimation is a real-time exercise. Load flow is not a real-time exercise. So I think I've tried to deliver whatever I knew. So, is it okay or
Okay, sir.
okay? Thank you. So that's the overview of these weeks lecture content, and we have the mostly it was mathematical because backward forward sweep load flow, so we can start solving the numerical, so that will give a better understanding, and question answers too. It's not only the previous assignments have a mix of the numericals as well as the assignments, the question answers. Okay, so let's start the discussions of the assignments. So, okay, So here it's question number 1. Okay. So if a small problem, so the distribution line resistance Okay, this is the question. If a distribution line resistance is 1.5 ohm, determine the per unit line resistance considering base kV equals to 11 and base MV equals to 100. Very small problem, so please do it fast. Okay, there are some options. Okay, so I will 1 point.
1.239.
It's the correct answer, but I forgot to give the options. Yes, 1.24 is the correct answer. I'll just write the options because later on you can access the PDF. Option A was 1.24, B was 0.015, option C was 413, and option D was 1.815. Okay, so yes, let's solve it very fast. So base value of the resistance we can obtain is, we can say ZB. Here no impedance is there, so it will be RB only. So it will be kV square by MVA. So 11 square by 100. And when we have the per unit value, so per unit uh, resistance, it will be actual by base. Actual by base. So base already we have obtained 11 square by 100 and actual is 1.5. Is it giving the same value? I have the calculator.
Yes.
Yes, 1.239. Yes, yes, 1.24. So that's answer. Okay. Moving on to the next question. If a distribution system line reactance 0.5 per unit, determine the base KV 11, base MVA is 100. Options are 0.413, B is 0.202, C is 50, D is 605. This is a question.
D, sir.
Which one? D.
D.
Ah, yes, D is correct. Marking that. Here the option was this one is correct. Here D is correct. Let me just solve it very fast. So we can say line reactance ohm is zero point 0.5 already given. So zero point 0.5 actual by base. Now base into per unit. So what is base? Base is 11 square by 100. So, so 0.605. So write the formula 2 because this is actual, this is base. So actual into base, that is, that will give, sorry, this is per unit into base, that will give actual per unit. This one is the, okay. So yes, this is the answer. So moving on to the next question. Which statement uh, find the correct statement in view of backward, forward, sweep, load flow. So is first line currents, line currents in forward sweep. Second, node voltage in backward. First line current in backward. So hmm. So which one is correct?
Second one.
Second one. Yes. So line currents in backward sweep and then node voltage in forward sweep. Next, the I'm writing LF, okay, for a load flow. This is load flow. So here I am writing load flow, but next I will use this LF. See load flow. And everything starts with guess value of hmm, the backward forward sweep load flow algorithm starts with the guess value of node voltages of load nodes, node voltages of slack node, load currents of load nodes, and load currents of slack node. Which one is correct? We need to take a guess solution. Yes.
A. Node voltage of load node.
Node voltages of load nodes. Yes. Number 5, I guess. Which of the following Which one of the following steps require more computation effort? Forward sweep, backward sweep, lateral sweep, downward sweep.
Backward.
Backward. Specified. The following parameters are specified for load nodes of radial distribution networks. Active and reactive power, voltage magnitudes, voltage angle, and power loss. Which one of the following parameters?
This is multiple answer or single answer?
No, single, single.
Then B.
Which one?
Voltage magnitude.
Voltage magnitude. Okay. Why
No, no.
are specified? Which of these parameters for the load nodes?
Load nodes. Active and first one.
First one, yes. For the load nodes, we are given the value of active and reactive parts. Okay, so P and Q given, and based on the P and Q we need to find out V and delta. That's our aim. So from using the, and these V and delta we choose the values like 1 for magnitude, the magnitude, and delta is the 1 angle 0. So 1 angle 0 is chosen is for the first guess solution, guess assumption, and then we can start our backward, forward sweep load flow, and then we obtain a result which gives the final outcome as the converged value based on the tolerance given for the maximum difference between the last iteration and this iteration for any one of the node. Okay. So if any one of the node violates, the convergence criteria won't satisfy. Okay. So P and Q is the answer. So active and reactive power is given for load nodes. This is 767. This is an MSQ. This is an MSQ question. What are the data of distribution lines required to perform forward backward sweep load flow algorithm?
B and C.
So B and C. So data of the distribution lines, right? So
B, A and B, A and B.
yes, line resistance and line reactances are required. I'm writing FBLF. Okay, so forward backward FBSLF, forward backward sweep load flow. I think it is clear, right? If I use this acronym.
Yes.
So Most the computation of forward backward sweep the computation of forward backward sweep load flow algorithm starts with the most distant node, substation or slack node, any intermediate node, or the node with least power demand.
B.
B, substation or slack node, right?
Yes.
Yes. Here it's a backward sweep. Backward sweep computation of forward backward sweep load flow algorithm starts with most distant node, substation or slack node, any intermediate node, or node with the least power demand. Previous one was the forward sweep. This one is backward sweep. Any answers? Previous one was forward sweep. This is for the backward sweep. Okay. So it should start with Any answers? So most distant node, right? Backward shift starts from the end node and moves towards the slack node or substation node, and forward shift, which is the current voltage sweep. The backward sweep is also can be stated as the current sweep, and the forward sweep can be considered as the voltage sweep. So it starts from substation node and backward sweep starts from the most distant node. So this is the question. The power demand of a node for a radial distribution network are 80 kilowatt and 60 kVAR. Okay. So base VA is 1 MVA. Compute the current phasor drawn by the load in per unit for the first iteration. So we have to compute for the compute in per unit for first iteration of the forward backward shift. These are the options. It will solve. Take 2-3 minutes.
Base kVA is required, sir.
Base kVA is what 1 MVA given.
One one 1 kV. Base kV.
Base kV is not required. We need to just calculate the power, right?
Yes.
So for the first iteration of a load node, we know the voltage values. It's 1 angle 0, right? So take 1 pu as the voltage value for the first iteration.
Yes.
Any answers? Otherwise, we'll solve.
Can we solve, sir?
Okay. So already we know that if no value is given, so for the first iteration we can choose the voltage values per unit. Okay. 1 angle 0 degree. Okay. Now, and we are required to find out current phasor. So I phasor, so that is P minus JQ G phasor conjugate, right? So, but these P and all these things needs to be in per unit, because V, once we have this V in per unit, so these things needs to be converted in per unit. And here 1 MVA is given, so base MVA is 1. 1, I guess. Yes, 1 MVA. So that can be equivalent to 10 to the power 3 kVA. So what we can do, and P, as we all know, that kilowatt, 80 kilowatt, if you convert it to per unit, just we need to divide 80 by 10 to the power 3. That will give the same value in per unit for the kilowatt. Means we need to convert it to per unit. So from kilowatt to per unit, just divide it by MVA for kW to per unit divided by kV. It will convert the same values to the per unit values. So this is a simple rule. So we just write 80 divided by 10 to the power 3 minus j 60 divided by 10.
That means that P is the actual value.
Yes,
Actual value by per unit value base.
this is the actual
P
value.
per, P per unit is calculating by P by actual base MVA.
It's base.
Okay.
And this one also by base. And this value is 1 per unit, 1 in the 1 angle 0. So 0 has no effect. So if we 0.08 minus j 0.06. So this is the answer. So here answer would be 0. Yes, this one D is the answer. Okay, this will give the current value. Okay, so moving on to the next set of problems. Just see whether it is visible to you or not. If it is, I try to zoom as much as I can. Then please solve. So the load and line data is given. Okay, these are the line data. This is the load data of a single phase distribution system. The voltage at bus 1 is 11 angle 0 kV, 0 degree kV. And the load flow problem is solved using backward forward, means the same backward forward C. Assuming initial voltages of the buses to be 11 kV, 11 angle 0 kV. So this is for bus 1, and initial gas values of the buses can be considered as 11 angle 0 degree kV. So just calculate the load currents I2, I3, I4 and I5, because how many nodes are there? What would be the connection diagram? Let's draw the connection diagram considering one as the substation node, this one as the substation node. From 1 to 2 there is a connection. From 2 to 3 we can see there is another one. Then 3 to 4 we have another one, and 2 to 5 there is another one. So this is the network radial distribution, and this is the from bus node voltage at bus 1. So this is given 11 angle 0 degree kV, right? So and consider the gas values of all the nodes as 11 angle 0 kV initial gas values. So and power for all these nodes are given. Power for all these nodes are given, right? P1 from power P1, 2, 3, and all these values load at bus J. So this means this is for the bus J. So bus J is 2 here. I think it's understood, right? Bus J. This row is for bus J means 3. This is for 4, and this is for 5. I think it's clear.
Can you repeat, sir?
Here it is given load at bus J, and what is J here? This one is J. So I have just written these values from J, right?
Okay.
2, 3, 4, and 5. So these are node values, node load demand values, you can say. So for bus 5, the load demand value is 300, and for P is 300, and Q is 100. Means you have the units. I have not written it here. For 4, P is 400 and Q is 300. For 3, P is 500, Q is 300. For 2, it is P is 200, Q is 100. So these are the node load values. Means the values of the, like, these these are the node loads. Indication of the node loads can be given as this, right? So this is the value or the load flow. This is the network or the radial distribution system network. Just P and Q values are given. So using this same formula, P and Q values are known and nothing is in per unit here. So just compute these same values using the same formula. P and Q values are known. Calculate I2. These are the load currents at buses. So bus injection currents are required. If you can find any one of these values, the first I2, calculate just I2, since it's an MCQ and all the options are different for I2 itself. So you can uh, find it out from there itself. But I would recommend that calculate for all, because but in exam, since all the options for A, B, C, and D, all the I2 values are different, so you can directly mark based on any one of the correct answers found. All are different. Shall I start solving?
Yes, sir.
Okay. So just we need to use the same formula, right? For I2, let's calculate for I2. So what will be I2? The node value, that is P2. If we say P2 plus JQ2 by V2, so whole thing needs to be conjugate, because power is equal to VI conjugate here, right? So P value is given. P value is 200. 200 minus, you can say, minus JQ. What is Q? 100. And V2 is 11. All are in kilowatt, kilowatt. So, and the voltage is also in kilovolt. So all this K gets cancelled in the numerator and denominator, and we are left out with 11 angle 0 here. So 0 has no effect. So, and already I have taken all these things out of this conjugate, means the numerator part. I have written here minus. So just calculate 22 200 by 11.
Sir, in previous problem we used P2 minus JQ.
Ah, yes, but there we didn't use the conjugate, right? So you could have used conjugate here itself. Without using that conjugate, I have directly written minus. So if you use the conjugate, if you use the symbol of conjugate here, then you should use plus.
Yeah,
So
that means in previous problem you put V2 conjugate.
V2 is conjugate there also and here also.
Here also, instead of there we used -1.
I am just writing in the same way so that no ambiguity is here. Is it fine?
Yeah, clear, sir. Clear, clear.
Hmm. The value, because only V magnitude is there, angle is 0, so the conjugate would have no effect on the denominator, right? But on the numerator side, it would become just simply minus. Okay. Same is the case here too. So just calculate, it's
Okay.
coming to 18 point something, 18 point, uh, 18.18 minus 100 by 11. 9.09, J 9.09. Now this is in rectangular, the answer is given in polar. So 20.32. This will be the magnitude and angle would be minus 26.56 degrees. Okay. So this is the current for I2. Is it clear?
Yes,
So
clear, sir. In examination, we can use this calculator,
that
scientific
will be,
calculator.
yes, yes, not, you can't use the physical calculator. That would be in the exam stream, the calculator would be there. So you'll have to use the mouse pointer to calculate.
Yeah, that is scientific. It's available or
Yes,
normal?
yes, yes, yes. Scientific would be available.
Okay, okay.
But you can't take the physical calculator. You'll have to use the digital one.
Yes.
So this is the current for I2. So already we have found out that option A will be correct because no other options are matching here. But since we are solving it here, so let's do it fast and I'm writing the final answer because of each one of them, the final answer I have. But for individually, I need to calculate. So that I had to do with the calculator. So E3 would be 500 and 300. So 500 minus J 300 by 11. So the answer would be 53.00 minus 30. 53 point. Option A is correct. So that's minus 30.96. So I4 this number plus. This one will be 45.45 angle minus 36.87 and I5 plus minus 300 and 100. For all these cases, denominator is 11 only and it's 28.75. Just check whether these are correct or not. I think uh, these will be correct. Okay. So option A is the correct one. Okay. So this is the questions. This part is same, but here we need to determine the line currents. What we had determined here were the node currents, right? So here the question is to find out the line currents for the first iteration only. Here it is line currents. Here it was the load currents. Okay. So I'm just redrawing the circuit so that will be of help. One, and from two there is a 5. For all of this, there are some loads connected. This is the substation. 1, 2, 3, 4, 5. So already we have these currents I5, I4, I3, I2. But here we need to find out I12. This will be I12, I12. This will be I23, I34, and I25. So please just find out any one value and match so that we can assure the answer and then move on to the next question, because the same would be the remaining part would also match accordingly because all the four options. So what will be I12? Just uh, say it in the notation form. What will be I12 from the circuit as shown? I12 will be summation of I12 will be the summation of which two currents or which three currents or which one current? This one.
I1 to yes 2 3 and 2 5.
2 3 and 2 5. So I23 and I25. So already, and now again there is a question that I25 will be which one?
Only I5.
Yes, only I5. So I25 already know. I25 is I5. That means this one 28.75 angle minus 18.43. So 28.75 angle minus 18.43, right? This is already been known. No. Now next coming to the value of I23. So I23, what will be I23?
I2 I3 plus I4.
Yes, but yes, for here it is same, but actually speaking, actually if we say the correct notation, it will be I3 plus I34. Although here I34 is I4 only, but notation wise if we go, and I34 will be I4. So here it will be I3 plus I4. So I34 is also known. I34 is only I4. So what will be I4? 45.45 angle minus 36.87 ampere. So already we know I34 and I3 value we already know from the previous one. I3 is 53 angle minus 30.96. 53 angle minus 30.96 plus I34. Just we need to place this value here. Just need to substitute this value here. So it will be 45.45 angle 36.87. So if we calculate these two, so once we can match the answers from here itself, but like I34. So last one is I34. So I34 is here. Two of the options are matching. So we can't decide whether based on the remaining part we'll have to decide the final answer. So I34 is this one, and I25. I25 is 28.75. Right. So yes, we can decide here option D, because this one is already known, this one is already known, this one is I25, this one is I34. So only these two are correct, and these two are correct here, and these two are only in option D, because here the option A, the I25 value is different, 53. So option B is correct, but you can, and once you find out the D is correct, you will have a idea how these values would be. What will be the values of I12? So I12 would be, I'm just writing the final form because there are remaining questions. So it will be 146.59 angle minus 29.74, and this one I23 will be 98.33 angle minus 33.69. Is it fine?
Yes.
Okay. So let's move on to the next question. I think it's visible. So here load and the upper part is the same. Here the bus voltages we need to determine respectively in kV of end of first iteration. So V2, V3, V4 and V5. So I'm drawing the circuit again here. So this is the substation node 1, 2, 3, 4, 5. So we need to calculate V2. So this is V1, V2, V3, V4, V5. So what will be V1 is already known. It's given 11 angle 0 degree, right? So what will be V2 based on the formula we have? Okay, let's start with V5, right? So what will be V5? Okay, oh, sorry, this is the voltage scene, na? So we'll have to start from the substation end. So what will be V2? Sorry. What will be V2? V1 minus
V1 minus
I12
into
Z,
R.
Z12, because R and X data both are there. Okay. Then V3, V3 is V2 minus I23 Z23. V5 will be V2 minus I25 Z25, and V4 will be V3 minus I34 and Z34. So all these values after the end of first iteration, we have the values of V1. So let's calculate for one, and remaining we can check. So 11 angle 0. So I'm just writing the value of 11 here. I12, what is I12? Already we have calculated. It's 146.59, 146.59 angle minus 29.74, minus 29.74, and Z12. So Z12 is, yes, bus 1 to bus 2. So zero point 0.4 plus zero point 0.6. So zero point 0.4. So here it is in polar form. So 0.4, 0.4 plus j 0.6. So this is in polar form. So we need to convert it to rectangular coordinate.
Z12 is given in table.
Yes, Z12 is given. Na? This R and X given.
Oh, yes, yes. Okay.
So from R and X we can compute the Z. So this is R 12. Just I'm writing so that it is clear. R12 and X12. This value and this value. So from here we can calculate the value, and so final value I'm writing because we have other problems to solve as well. So for V2, the answer would be 10.905 angle minus 0.25 kV. So just check once whether the values are correct or not. I think it will be correct because I've taken from the answer, final answer given. So just check once. So after finding this one, so we can clearly see that only option C is matching. Okay. So similarly, we need to find out the values of V3, V4 and V5, and those values would be these 10.859, 10.841 and 10.897. So one thing we can understand that once we are at the substation node, we are having a kilovolt of 11. When we are going downstream at node 2, we are in 10.905. I'm writing only the magnitude, not going to the angle. And we are going to node number, this one is V3, node number 3. So it is further reducing, the node voltage is further reducing. As we are going towards node 4, it is further reducing. But as we go in node 5, since we have only one line here, so the value of node value could have reduced, but since based on the line parameters, the value is still in a good shape as compared to these value. If we compare these two, we can see this one because the line, the impedance is far less as compared to the total line impedance getting added while we are moving from 2 to 4. So that's the analysis where we can see. So these are the voltages in kVs. Okay, so this is the options. V2 is correct. So V2, as we have calculated, this one is correct. So V3, V4 and V5, just you refer from option C. C, no? C. So process is similar. Formula you should use all this, and for all these cases, initial guess values are, so starting values of V2, V3, because these three values are required, right? V2, V3. So all these three values have a initial guess start of 11 angle 0 kV. So just use that value. V2, V3 are having the same value of 11 angle 0 kV. So That will give the final answer. Okay. Option C is correct. So moving on to this question, just see.
That means V2 V3 first time 11 angle 0.
Yes.
First
No.
it's
Sorry. Oh, that we need to ensure, na? Okay. So, already, no. Because already V2 we have calculated, na? So,
Yes.
while going downstream, sorry, my mistake. So already we have calculated V2. So, just,
Yeah,
sorry.
V2 is 10.905.
Yes. We just need to use this V2 here. This V2. Just use this V2 and calculate this V3. Okay. And once we have this V3, just put in the value of V3. With this V2 would be same for both. V2 would be same for both. And for V3, just use this value of V3 obtained here. Okay. Now is it clear? That was my mistake from my side.
Clear.
Okay. Thank you. Thank you for pointing out. Sorry. So this is question. The connection diagram is nearly similar, but let me draw it once. So one node gets added. Substation node. Okay. So this is 1, 2, 3, 4, 5, and this is 6. Node 6. These are the loads. Okay, these are the loads. But here the bus voltage, bus 1 kV is 11 angle 0 kV. This is same as that of the previous one. But what are given is the line flows are given. Means the line currents are given. Okay. And what we need to find out is question number. It's, let's say, question number 6. Although it's not 6 here. So determine voltage in kV for bus 5. That's the question. Determine the voltage in kV for bus 5. So how to compute the voltage for bus 5? Just say it in the mathematical equation form and we can finally get the values. But before that, let me just write it. This is I12, I23, mathematical notation we just say so that things becomes clear. I45, and this is I36, right? So, and these values are given. This is I12, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 3 to 6. All these I values are given. And initial voltage start for bus 1 is also given 11 angle 0 kV. So just we need to, and the line impedances are also known here. Same formula, but and just need to calculate the line flows. There we had to calculate the line flows individually, and then we could have used that to get the final values of voltages. But here directly initial voltage is given and the line flows are also given, right? So voltage, what will be the voltage for bus 5? voltage is starting from substation node. So V2 will be V1 minus uh, I12 Z12. V3 will be V2 minus I23 Z23. V4 will be V3. I34 Z34. V5 will be V4 minus I45 Z45, right? And V6 will be V3 minus I36 Z36. So here we are required to find out this value, and V4, for finding V4, because V4 is not known to us, we need to calculate V3. To use V4 we need to know V3. To use V3 we need to know V2. Only known is V1. So we will have to do all these four steps. So 11 angle 0 minus I12 is given. What is I12? 235.98. The angle minus 26.64. And Z2 is also given. Z12, sorry, not Z2. Z12 is 0.2 plus J 0.3. 0.2 plus J 0.3. So if you just calculate, you will get the value of V2. Just use these V2 here, just use V3 here, and finally V4 here. So that will lead to the calculation of V5, and this is the desired result, this is desired answer, right? This is required, bus 5, that is V5. So is it clear, right? So you can calculate.
Yes, clear.
Yes. So I'm writing the final value of V5, right? If it is clear.
Yes, sir.
Okay. Because Z23, all these values are available. All these values are available from the table. Available in the table. Just compute the values, and V2 and V3 we are calculating step by step. Every step we are getting one value. So the final value of V5 is 10.521 angle minus 1.61 kV. So this is the final answer. This is the final answer. Okay. This is the final answer of 6. Now moving to question 7. Is it clear, the previous one?
Steps is clear.
Okay. So next question is, determine active load in kilowatt at bus 4. So at bus 4 we need to find out the active load. So that means there are some P and Q values for each of these nodes. P and Q, this will be P4, Q4, P4, Q4, P5, Q5, P6, Q6, P2, Q2, P3, Q3. So for all these values, here we are required to find out the value of bus 4, that means P4, active power at bus 4. P4 we need to calculate. So how to calculate P4? How to calculate P4? So P4 we can calculate. So what is P4? P4 is bus power, not power injection, right? So V4, I4 conjugate, and V4 can be obtained from this one. V4 can be obtained from the same steps. So V4 means V3 minus I34 Z34, I34 Z34, and to obtain V3, this is V4, but we also need to calculate V3. So V3 will be V2 minus I23 Z23. So V2 minus I23, and V2 is again given. V2 is V1 minus I12 Z12. So we need to follow the same steps. This one is known, 11 angle 0 kb, and I12. All these values are obtained, can be obtained directly from the table itself. All these values. So all these values can be directly referred to the table. So once we calculate V2, just same step. V2 calculate, just place it here. Then calculate V3, place it here. Just we can find out V4. So this is this V4. So we can use V4. And what is I4? I4 is I4. This one will be I4, right? So I4 will be summation of which two current? I4 will be, if this is I4, I4 will be the current. What will be I4?
I4, I45.
So I4 will be, I4 is flowing here, right? I4 is flowing here, and I34 is flowing here, and I45 is flowing here. We have the information of I34 and I45. So what will be I4? Just apply.
I34. I34.
No, I4 is, means this is node number 4, this is node number 5, this is node number 3, and from 4 we have a load connected here. This is drawing a current of I4, and there we have another node where the current is drawn is I5, and the current flowing, line current flowing is I34 here, and line current flowing which is same as I5 itself. So we can say it I45, or I45 is same as I5 itself. So what will be I4? Just apply KCL here.
Yeah. I34 minus I45.
Yes, yes, yes. KCL at node 4. So I4 will be I34 minus I45. So 45 is given here. I45 is this one, I45, and I34. I34 is this one. So from here we can directly calculate I4, right? So I4 will be I34 minus I45. Again, these two values are again given in the table itself. These two refer from the table itself, right? So I4 is also calculated. So just we need to place this I4 here and that V4 here, and we'll get the final value. So I'm writing the final value, right?
Okay.
Is it clear? No? It's the procedure I'm trying to, because the calculation you can do yourself. I'm just trying to.
Procedure.
So the value, final value would be 871 kilowatt. Okay. This will be the final answer. Do check once. If the same value doesn't come, next day we can. But I think this is the answer, final answer given. So P4 is, this is the final answer. So similarly, next question is to find the kVAR at bus. Okay, so here it will not be just this one. One thing I missed. Here it will be the apparent power. So we will need to just use the real part to get the real power, because the question is to find the real power. Okay, so this is only the real part should be used, and the next question is to find the reactive power. So question, I think it is for 8. So determine the reactive load kVAR at bus 4. So same question, same everything. Already we have obtained the value of apparent power. So just we need to calculate here Q4. So Q4 can be, so we can write Q4 as imaginary of VI conjugate. But nothing else. Oh, sorry, V4I4 conjugate. Imaginary of V4I4 conjugate. Nothing else. Already we have found out the values there. So the imaginary value would come, the Q4 value would be 185 kVAR. Is it clear?
Yeah. How it is 185, sir?
Okay, already we'll get the values. This is if we use V4I4 conjugate, that will give the apparent power. From here already we have calculated that. Okay, so
Yeah.
just we take the real part, that will give 871, and this one is the apparent power. This one is the apparent power. Apparent power. So V4, this is this V4 only, this V4, and I4 is this I4 only. So V4 and I4 we have obtained from the previous I4 and V4. Okay,
Yeah, do it.
is it fine?
Yes, sir.
So
But
only
how actual calculation, how it is coming? Yeah.
Actual calculation, yeah.
871. Okay.
This is V4, na? Already we have discussed. First we need to calculate V2. This is the step by step. First V2, then V3, then V4. Once we get V4, this is one of the values that we require to calculate the apparent power. Again, I4 is obtained from I34 minus I45, and for all these values, these are given in the power flow values in the table. These are the power flow values, line current flow values are given in the table. These are the line current
That
flow.
means while calculating, we will get the imaginary part we have to use.
Only just imaginary. Only for this question, this is for question number 7. It is the active power. For question number 8, it is the reactive power. So real part of this V4I4 is the active power, and imaginary part of this V4I4 would give the reactive power. Nothing else we need to do.
Okay. Okay.
Same thing. For in the previous calculation itself, we will get the apparent value. Only take the real part to get the real power. Only take the imaginary part to get the imaginary power. No, sorry, reactive power. Nothing else. Calculation remains the same as the previous one.
Clear, sir.
Yes, yes. So the next question is determine the line power loss between bus 2 and bus 3. So what will be the line power loss between bus 2 and bus 3? This is bus 2 and bus 3. What will be the line power loss between bus 2 and bus 3?
I square result.
I square R. So only just I23 value is already known here. This is I23 value. Is it fine?
Yes.
So power loss between this line is I23 square R23, right? So
No
I23
need to take as result there. Only R is enough.
only
R is enough.
only
X
R
is
is
not
enough.
required.
Only R is enough. Yes, only R is enough.
Power loss.
Power loss
If it is voltage drop, we will take I23 into Z
I23 into Z
for voltage drop. Here
for
power
voltage.
loss I square.
This is only for power loss, real power loss. Power loss would be real power only. So I23 into I23 square into R23. So I23 is known directly. You can refer and R23. What is R23? This one is R23.4, and I23 is 200.63. Okay, just let me these two right. 200.63 whole square into 0.4. Is it fine? This will give the final value of 16 kilowatt. Is it okay? 200.63 is this one, magnitude. Is it fine?
Yes, sir.
And this is the R23, this is I23 magnitude. So this is the final value. So this is the answer. This is the final answer. This is also the final answer. So on the last question, determine the total power loss. Kilowatt in the distribution system. So total power loss will be what? Total power loss. So here we are required to find out the total power loss.
Then total current square into resistance.
No, individually we need to find out. Na? If we totally make the current
Yeah.
sum of individual square into
Into
resistance part. So first total current is I loss, right? I loss total is I23 for the first one, 23 into R23. Then I34 square R34. Then I45 R45. And then one was there in between I36. 2, 3 done. Oh, I12 I have not taken. Na? I12 into R12 you should also take, and then I36 R36, I36 R36, 1, 2 and 36 plus I12 square R12 plus I36 square R36. Is it fine? 5 branches are there, so 5 losses would be there. 1, 1, 2, 3, 4 and 5. So 5 lines are there, total 5 lines. So sum of these 5 lines would give the total loss. Is it fine?
yes, sir.
Yes. So, and all these values we have directly in the table, right? All these values, directly we have all these values in the table. All the current values are also there and all the resistances. So, I am not writing all these values here. So, all these values can be directly referred from the table. Is it fine? I23, I23, all these currents are given. I23, I34, this one is I36 and this one is I12. So all these notations are written here. So you can just put all these values here, and similar is the case for R. This one is, let me write it here only, R12, R23, R34, R45 and R36. So just put all these values there in the last equation and get the total loss. So the total loss will be around 54 kilowatt. Okay. So this is the final answer. Is it fine? All these values can be R and I, all the values, that is, let me write it here, current and resistances, I and R. All these values can be referred from the table. Is it fine?
Yes, sir.
Okay. So that's it from my side. So if you have any doubt, you can ask. Otherwise, we can end today's session. That's all I had from my side.
Okay, thank you, sir. It is clear.
Okay, thank you. Thank you very much for attending the session. Okay. We'll meet on next Tuesday. I'll upload all these things. Okay. You just check and see. I have tried to mention all the values. If it is not clear anyhow, we can't solve all this because these are very detailed numerical problems. But just try to get the values. At least have the idea of what these how these calculations proceed. So that uh, backward forward sweep load flow gets much clearer. Okay then. So thank you for attending. Okay.
Thank you, sir.
Okay. Good night.